So let us talk about light and color. We'll see reflection and refraction, mirror lenses and the images, and the optical systems. So start with reflection and refraction. The key question is always, how do we describe the reflection and refraction of light? This is how you see yourself on a mirror, and this is only possible because of reflection of light. The overall study of how light behaves is called optics, and the branch of optics that focuses on the creation of images is called geometric optics. So overall study of light is optics, and the branch of optics which deals with the creation of images is called geometric optics, because it is based on relationship between the angles and lines that describe these light rays. So a lens is an optical device that is used to bend light in some way, in a specific way. A converging lens bends light so that light rays come together to a point. That means the light ray converge. And the diverging lens, this bends light so that it spreads light apart instead of coming together. This is an example of converging lens. These are the light rays, this is the magnifying glass. And see how when we converge all the energy or light, the energy becomes so high that the paper catches fire. Now, mirrors reflect light and allow us to see ourselves. As I just mentioned, a prism is another optical device, prism, that can cause light to change directions. Prism to change directions. A prism is a solid piece of glass with flat polished surfaces. Right? This is a prism. These are the basic optical device. We have converging lens, we have diverging lens. See, the images are converging, images are diverging. This is a mirror and this is a prism. So images appears in mirror because of how light is reflected by mirrors. The incident ray follows the light falling onto the mirror, and the reflected ray follows the light bouncing off the mirror, like this. Okay? And in specular reflection, each incident ray bounces off in a single direction. Specular reflection, ray bounces off single direction. A surface that is not shiny creates diffuse reflection. So what happens in this diffuse reflection? A single ray of light scatters into many directions. This is specular reflection. Incident ray bounces off in a single direction, and a surface that is not shiny creates a diffuse reflection. This is a diffuse reflection. So in this diffuse reflection, a single ray of light scatters into many directions. Now, law of reflection. The incident ray strikes the mirror. The reflected ray bounces off, and the angle of incidence is always equal to the angle of reflection. So incident ray, this is a mirror, this is a reflected ray, and this is the normal. These two angles will always remain equal. That means angle of incidence will be equal to angle of reflection. Law of reflection. A light ray is incident on a plane mirror with a 30-degree angle of incidence. Need to sketch the incident and reflected ray and determine the angle of reflection. So pretty simple. This is 30 degree. So this will also be 30 degree. Now coming to refraction. A light ray may bend as they cross a boundary from one material to another, like from air to water. The bending of light ray is known as refraction. This is how you see your straw from outside, because this is the refracted image of straw. You see, it is bent inside the water. So the light rays from the straw are refracted or bent when they cross from water back into the air, because when it reaches your eyes, it seems bent. So when a ray of light crosses from one material to another, the amount it bends depends on the difference in index of refraction, which is also called refractive index between two materials. So refraction from air into diamond, refraction from air into water. See, air has a refractive index of 1, whereas the diamond has a refractive index at 2.42, water is 1.33. So diamond bends the light ray more than it is done by water, but still it bends. So the ability of material to bend rays of light is described by the index of refraction or refractive index. These are the values, the index of refraction of various material. So vacuum 1, air 1, almost 1, water 1.33, ice similar to water 1.31, glass 1.5, diamond 2.42. This is how refraction is seen. Light rays incoming. This is the angle of refraction. This is the angle of incidence. This is the angle of refraction. So refraction from air into glass, air, glass, then coming again to air. Now Snell's law of refraction. This Snell's law is very important as far as refraction is concerned. Snell's law is the relationship between the angles of incidence and refraction and the index of refraction of both materials. This is Ni sin theta I is equal to Nr sin theta R. This is Ni, index of refraction of incident material. This is angle of incidence in degrees, theta I. This is index of refraction of refractive material. This is the angle of refraction. This is the Snell's law. So let us calculate the angle of refraction. A ray of light traveling through air is incident on a smooth surface of water at an angle of 30 degree to the normal. Like this, 30 degree to the normal. Now we need to calculate the angle of refraction from the ray as it enters the water. How to do it? Just you use N1 sin theta 1, that is sin 30 degree, is equal to N2 1.33 into sin phi or sin theta. You will compute the sin theta or phi using Snell's law. This is reflection and the critical angle. Now at one point the refraction is not possible, means the refractive index becomes, the difference of refractive index becomes so large, the ray has to reflect, means total internal reflection takes place. This is the angle beyond which there is no refraction, only reflection. This is called a critical angle. Now dispersion and prism. This is a normal light, or you say this is a white light. When it comes out of prism, you can see various vibrio light out of it. So when light or white light passes through a glass prism, blue is bent more than the red. Blue is bent more than the red. This is why, because the lambda or wavelength of blue is higher than the red one. So colors between blue and red are bent proportional to their position in the spectrum. These light rays do not reach our eyes. These are the light rays. But these light rays do reach our eyes. So white light from sun, therefore we see a kind of rainbow when it is bright rainy day or just after rain. You will be able to see this refractive phenomena. So the variation in refractive index with color is called dispersion. A rainbow is an example of dispersion in nature. The tiny rain droplet act as a prism separating the colors in the white light rays from the sun. When coming to mirrors, lenses and images, the key question is, how does a lens or mirror form an image? This is exactly in the similar fashion as your eye does. When you see a world of images created on the retina of the eye by the lens in front of the eye. So this is the retina with rod and cone cells, which sends the information to the optic nerve. Here we have a lens, right? This is the cornea, this is iris. So objects are real physical things that give off or reflect light rays. Images are pictures of objects that are formed in space where light ray meet. This is actually your image. If you see through telescope, these are the actual object and this is what you see. So the most common image we see every day is our own reflection in a mirror. The mirror or image on this mirror is called a virtual image because the light ray do not actually come together. The virtual image in a flat mirror is created by the eye and the brain. The light rays that enter a converging lens parallel to its axis bend to meet at a particular point called the focal point. These light coming from say infinity are converged through a lens to a focal point. So this is the focal length. Distance from the center of the lens to the focal point. This distance is called the focal length. And the optical axis usually goes through the center of the lens. This is the focal point, this is the focal point, this is converging lens, this is diverging lens. So the image formed by a lens can form a virtual image just as a mirror does. Rays from the same point on an object are bent by the lens so that they appear to come from a much larger object. Right? This is how you see your thumb enlarged. This is the ray. Actual images like this, virtual images like this. This is the object and this is how it is formed. This and these lights, they intersect here and they will make your thumb feel larger. So a converging lens can also form a real image. So in a real image, light ray from the object actually come back together. Like this. This is the object, this is the image which is actually a real image. And this is the ray diagram. So drawing ray diagram is the best way to understand what type of image is formed by a lens and whether the image is magnified or inverted. So these three rays which we'll be showing follow the rules of how light rays are bent by the light. First of all, a light ray passing through the center of the lens is not deflected at all. A light ray parallel to the axis passes through the far focal point and a light ray passing through the near focal point emerges parallel to the axis. So this is how we set up. This is the object, this is our lens, and we draw the first ray, means from the center to the top of the object. And this is drawing the second ray, means because if it is parallel to the axis, it will go through the focal point. Now this is the image. We join the point where they intersect to the horizontal axis. So these are the images, right? If it is here, you see it becomes like enlarged. And if this is a diverging lens, this is the action which is taken. So converging lens, which is position is beyond the focal length, then the real image will be seen. And converging inside the focal length, virtual and larger. And if it is diverging anywhere, if you see virtual and smaller than object. Coming to optical systems, how are the properties of images determined? This is the digital camera. This is the CCD image sensor. So optical system is a collection of mirrors, lenses, prisms, and other optical elements that perform a useful function with light. Characteristics of optical systems are the location, type, and magnification of the image, the amount of light that is collected, and the accuracy of the image in terms of sharpness, color, and distortion, and the ability to change the image like a telephoto lens on a camera, and the ability to record the image on a film or rather digitally, electronically. So the sharpness of an image. If defects in the image are called aberrations and can come from several resources. So ray or red ray comes, focus here, blue ray, focus here, right? So chromatic, this is where it should be. This area is a blur area. So chromatic aberration is caused by dispersion when different color focus at different distances from the lens. While spherical aberration causes a blurry image because light ray farther from the axis focus to a different point than rays near the axis. The rays far from the axis and rays close to the axis. Then comes the diffraction. This diffraction causes a point on an object to focus as a series of concentric rings around a bright spot. Thin lens formula is a mathematical way to do ray diagrams with algebra instead of drawing lines on a graph paper. This is given by 1 by d0 plus 1 by d1 or di is equal to 1 by df. do, di, df can also be represented by fo, fi and fd. This is object distance, this is image distance, and this is focal length. How to use this formula? Calculate the location of the image if the object is 6 cm in front of converging lens with a focal length of 4 cm. So this is 6 cm, this is 4 cm. What we have to do? Just use that formula and you can find, just you have to use this formula easily. You can find, because this do is given, you have to find di. So a technique known as image relay, this image relay is used to analyze an optical system made of 2 or more lenses. So the application, there are telescopes also, objective lens eyepiece, objective lens eyepiece. So you can view a distant object. So this was a basic idea about the light and color and little bit of optics.